In the vast darkness of space, 13.5 billion years ago, something impossible happened. Galaxies massive as our own Milky Way blazed to life when the universe was barely 300 million years old. This shouldn't exist according to everything we know about cosmic evolution. We're about to journey through 26 discoveries that have left astronomers questioning reality itself. You'll witness universe breakers, phantom galaxies, and cosmic mysteries that demand we rewrite the laws of physics. If you're curious about the cosmos, hit that like button and share where you're watching from, whether you're in New York during your evening commute or relaxing in Tokyo before sleep. Your engagement helps this educational content reach fellow stargazers worldwide. A galaxy named JADIS GS-C14-0 blazes across James Webb sensors like a cosmic lighthouse. This single point of light carries a message from when our universe was just 300 million years old. To put this in perspective, if the universe's entire history was compressed into 1 year, this galaxy appeared on January 22nd. Scientists expected to find cosmic babies at this distance. Instead, they discovered a galactic giant already mature beyond explanation. This galaxy contains millions of stars that somehow formed, lived, and died fast enough to create heavy elements like oxygen. The chemistry readings show concentrations that should have taken billions of years to develop. George Ricke from the University of Arizona calls it genuinely mind-boggling. The galaxy must have started forming stars immediately after the Big Bang ended. There was no warm-up period, no gradual build-up. Stars began igniting in the cosmic darkness almost instantly. The discovery required over 200 hours of telescope time, focused on a patch of sky smaller than a grain of sand held at arm's length. Every photon captured by Webb's mirrors traveled for 13.4 billion years to reach us. These ancient light particles carry information about conditions when the universe was barely 2% of its current age. Webb's infrared vision pierces through cosmic dust clouds that would blind other telescopes. The galaxy appears red-shifted, its light stretched by the expanding universe during its incredible journey. Astronomers measure this stretching to determine distance and age with startling precision. What makes this discovery disturbing is the timeline problem. Current physics models predict galaxy formation should follow a careful sequence. First, dark matter clumps together under gravity. Then normal matter falls into these invisible scaffolds. Gas clouds slowly collapse and ignite into the first stars. Those stars must live their entire lives, explode as supernovas, and scatter heavy elements across space before second-generation stars can form. This process should take at least 1 billion years, according to every computer simulation ever run. Yet here stands proof that massive galaxies achieved full maturity in less than 1/3 of that time. The universe somehow skipped several critical steps in its own rulebook. The James Webb Telescope essentially functions as a time machine. Looking deeper into space means seeing further back in time. This particular galaxy represents the most distant confirmed object ever observed by human technology. We are literally witnessing the universe's earliest childhood, and it appears nothing like what any scientist predicted. The implications stretch far beyond one unusual galaxy. If JADIS GS-C14-0 formed this quickly, how many other cosmic rules need rewriting? The deeper Webb looks, the more questions multiply like stars across the night sky. But this impossible galaxy represents just the beginning of our journey into cosmic mysteries. 6 galaxies hover in Webb's field of view, like cosmic criminals caught in the act. Astronomers have nicknamed them universe breakers because they violate the fundamental laws governing galactic formation. Each one measures more than 10 billion times as massive as our Sun, yet they existed when the universe was barely 500 million years old. Mike Boylan-Colchin from the University of Texas studies these galactic rebels with growing concern. According to every cosmological model ever created, these objects simply cannot exist. The standard model of cosmology, called lambda CDM, has guided our understanding since the late 1990s. These 6 galaxies threaten to topple decades of established science. The mass measurements seem impossible to dispute. Spectroscopic analysis reveals each galaxy contains stellar populations equivalent to 100 billion stars. Our own Milky Way galaxy needed 13 billion years to accumulate 60 billion stellar masses. How did these ancient galaxies achieve nearly double that mass in 1/20th of the time? Computer simulations consistently show that early universe conditions prevented rapid galaxy formation. Dark matter halos, the invisible scaffolding that holds galaxies together, required millions of years to grow large enough to capture significant amounts of normal matter. Gas clouds needed additional time to cool and collapse into star-forming regions. Yet these universe breakers appeared to ignore every constraint. They converted nearly 100% of their available gas into stars. Modern galaxies typically manage only 10% efficiency in this process. Such perfect conversion rates push against the theoretical limits of stellar physics. Joel Lager, an astrophysicist at Penn State, describes the revelation as upending settled science. The research team has been informally calling these objects universe breakers, and they continue living up to their name. Each new measurement confirms their impossible existence. The discovery originated from the Cosmic Evolution Early Release Science Survey, a multi-institution project led by Stephen Finkelstein. The survey examined a region of space roughly equivalent to viewing the moon through a drinking straw. Within this tiny sample, 6 massive galaxies appeared where none should exist. This raises a terrifying statistical question. If such rare objects appear in every small patch of early universe, how many more universe breakers lurk beyond our current detection limits? The total number could reach into the millions across the entire observable cosmos. 3 possible explanations emerge from this cosmic crisis. Either our understanding of dark matter evolution requires complete revision, or unknown physics governed star formation in the early universe, or the fundamental expansion rate of space itself differed dramatically from current predictions. Each possibility demands rewriting major portions of cosmology textbooks. The universe breakers force scientists to confront the uncomfortable reality that our cosmic models may be fundamentally flawed. The James Webb Telescope continues monitoring these galactic rebels, gathering additional data to confirm their impossible properties. Every new observation deepens the mystery instead of resolving it. However, even more puzzling objects await discovery in the cosmic depths ahead. Thousands of tiny crimson objects pepper James Webb's deepest images like scattered drops of blood across the cosmic canvas. Astronomers call them little red dots, a nickname that barely captures their profound mystery. These miniature galaxies appeared less than 1.5 billion years after the Big Bang, glowing with inexplicable brightness. Dale Kuchevsky from Colby College admits scientists feel confounded by this new population of objects. The little red dots challenge every assumption about early galaxy evolution. They measure smaller than typical galaxies, yet outshine objects 10 times their size. Their intense luminosity suggests something extraordinary powers their cause. Each little red dot spans roughly 1,000 light-years across, making them compact by galactic standards. For comparison, our Milky Way stretches 100,000 light-years from edge to edge. Despite their small size, these objects emit more light than galaxies containing billions of stars. The red coloration provides crucial clues about their nature. Infrared observations reveal specific wavelengths characteristic of hydrogen gas moving at tremendous speeds. This signature indicates material swirling around supermassive black holes at velocities approaching 10% of light speed. The black hole hypothesis creates its own set of problems. Supermassive black holes typically require millions of years to grow from stellar mass seeds. They gradually accumulate matter by devouring nearby gas clouds and unfortunate stars. The process follows predictable patterns observed throughout the modern universe. Little red dots seem to host fully mature black holes, weighing millions or billions of times more than our Sunday. These cosmic monsters achieved their enormous masses when the universe was still in its infancy. Current theories cannot explain how black holes grew so large so quickly in the early cosmos. Recent spectroscopic analysis confirms that many little red dots contain actively feeding black holes. The gas surrounding these objects shows clear signs of extreme heating and acceleration. Temperatures reach millions of degrees as matter spirals toward the event horizon. The feeding process releases tremendous amounts of energy across all wavelengths of light. This radiation pressure should actually prevent additional matter from falling into the black hole, creating a natural limit on growth rates. Yet these ancient black holes appear to violate this fundamental constraint. We observe nothing comparable to little red dots in the nearby universe. They represent a completely extinct class of cosmic objects that thrived only during the universe's earliest epochs. Their disappearance raises questions about what catastrophic events ended their reign. The sheer number of little red dots suggests they were common features of the primordial cosmos. Nearly every deep field image from James Webb reveals dozens of these mysterious objects scattered across vast distances. Their abundance implies that supermassive black holes played a dominant role in early galaxy formation. This discovery forces astronomers to reconsider the entire timeline of cosmic evolution. If black holes could grow to enormous sizes so quickly, they may have influenced star formation and galaxy development far earlier than previously imagined. The little red dots represent just one piece of an increasingly complex puzzle that James Webb continues to assemble with each observation. A team of astronomers at the University of Missouri stared at their computer screens in disbelief. 300 objects blazed across James Webb's infrared images with impossible brightness. These cosmic ghosts appeared where nothing should exist, challenging fundamental assumptions about the early universe. Haojing Yan, the lead researcher, describes these mysterious objects as candidate galaxies from the universe's infancy. The qualifier candidate reflects the team's uncertainty about what they actually discovered. These objects shine far brighter than early galaxies should be capable of achieving. The detection process resembled cosmic archaeology. Scientists applied sophisticated techniques, including infrared imaging, dropout analysis, and spectral energy distribution fitting. Each method confirmed the same impossible result: 300 objects violating the laws of galactic evolution. The brightness measurements tell a disturbing story. These objects emit light equivalent to galaxies containing hundreds of billions of stars. Yet they existed when the universe was barely 5% of its current age. The timeline allows insufficient time for such massive stellar populations to form and mature. Standard cosmology predicts that early galaxies should appear faint and small. The universe's expansion stretches their light across billions of years of travel time. Ancient galaxies should register as barely detectable whispers from the cosmic past. Instead, these 300 objects scream across space with bewildering intensity. The discovery required painstaking analysis of James Webb's early release observations. Astronomers examined every pixel of deep space images, searching for objects that disappeared when viewed through specific filters. This dropout technique identifies extremely distant galaxies by their characteristic light signatures. What emerged from this analysis defied all expectations. Instead of finding a handful of faint early galaxies, the team uncovered 300 blazing beacons. The statistical odds of such a discovery occurring by chance approach zero. Something fundamental is wrong with our cosmic models. The objects span a range of distances and ages, but all share the same impossible property: excessive brightness for their era. Some appear as they were just 400 million years after the Big Bang. Others date to 700 million years post-creation. All violate the predicted luminosity limits for their respective epochs. Bangjeng Sun, the study's co-author, emphasizes that spectroscopy will provide the final test of their findings. This gold standard technique splits light into component wavelengths, revealing precise information about distance, age, and composition. Only spectroscopic confirmation can determine whether these objects truly represent ancient galaxies. One object has already passed this crucial test, confirming its status as an early galaxy. However, this single verification leaves 299 cosmic ghosts awaiting analysis. The spectroscopic follow-up process will require months or years of additional telescope time. The implications extend far beyond these specific objects. If even a fraction prove to be genuine early galaxies, cosmology faces a fundamental crisis. The standard model of cosmic evolution would require major revisions or complete abandonment. These 300 ghosts represent either the most important astronomical discovery in decades or the largest systematic error in observational history. The truth awaits in the cosmic darkness beyond. In Galaxy UH Zone, something impossible lurks at the cosmic center. A supermassive black hole, weighing 13.2 million times more than our Sun, dominates this ancient galaxy. The monster existed when the universe was only 800 million years old, far too early for such giants to exist. This discovery came from combining James Webb's infrared vision with the Chandra X-ray Observatory's penetrating gaze. The black hole announces its presence through high-energy radiation as it devours surrounding matter. X-ray emissions provide unmistakable evidence of material heating to millions of degrees before crossing the event horizon. Traditional black hole formation follows a predictable timeline. Massive stars exhaust their nuclear fuel and collapse into stellar mass black holes, weighing 10 to 50 times the Sun's mass. These seeds then slowly accumulate matter over millions of years, gradually growing into the supermassive monsters that anchor modern galaxies. The growth process faces natural speed limits imposed by physics. As matter spirals toward a black hole, friction heats the material until it glows with intense radiation. This light creates outward pressure that opposes the black hole's gravitational pull. The result is a cosmic speed limit called the Eddington limit that restricts how quickly black holes can feed and grow. Even if early black holes somehow violated this limit and fed continuously at maximum theoretical rates, they still could not achieve supermassive status in only 800 million years. The mathematics simply does not work within known physics. Yet here stands proof that nature found a way around these fundamental constraints. Roberto Maiolino from the University of Cambridge led the team that confirmed this ancient black hole's existence. Spectroscopic analysis revealed extremely dense gas, moving at thousands of miles per second around the galactic core. These velocities require a gravitational field so intense that only a supermassive black hole could generate such forces. The black hole's host galaxy, designated GNZ 11, had puzzled astronomers since its discovery by the Hubble Space Telescope in 2016. The galaxy appeared unusually bright for its extreme distance and age. Webb's detailed observations finally revealed the source of this mysterious luminosity, a supermassive black hole actively feeding on surrounding gas clouds. This finding suggests that supermassive black holes played crucial roles in early galaxy formation. Rather than gradually developing after galaxies formed, these cosmic monsters may have emerged first and shaped galactic evolution from the beginning. The black holes could have acted as gravitational anchors, drawing in matter and triggering rapid star formation in their vicinity. The discovery of one supermassive black hole in the early universe implies that many more await detection. If such objects were common in the cosmic past, they may explain other puzzling observations from James Webb. Ancient galaxies that appear too massive, too bright, or too chemically mature might all trace their unusual properties to central black holes. However, This explanation creates new mysteries about how these early black holes formed in the first place. Without sufficient time for traditional growth mechanisms, alternative formation pathways must exist. The search for these cosmic time travelers has only just begun. Oxygen atoms float through the ancient galaxy JDS GS Z140 in quantities that should not exist. This simple chemical element tells a story of impossible stellar evolution, occurring when the universe was barely 300 million years old. The presence of oxygen this early in cosmic history breaks fundamental rules about how elements form in space. Oxygen creation requires a complex stellar life cycle that should take hundreds of millions of years to complete. Massive stars must first ignite, burn through their nuclear fuel, and explode as supernovas. Only during these catastrophic explosions do stellar cores forge oxygen atoms and scatter them across space. Second-generation stars then incorporate these heavy elements into their own formation process. Jakob Helton, the lead researcher studying this ancient galaxy, describes finding substantial oxygen as genuinely shocking. The measurements indicate the galaxy had been forming stars for potentially 100 million years before Webb observed it. This pushes star formation back to within 200 million years of the Big Bang itself. The timeline creates an impossible puzzle. If this galaxy contains significant oxygen, it must have already completed multiple generations of stellar evolution. First-generation stars needed time to form, live their entire lives, and explode. Then second-generation stars had to form from the enriched gas clouds left behind by those explosions. George Rieker, the study's senior author, emphasizes the complexity of this chemical cycle. Stars must evolve and explode as supernovas to release oxygen into interstellar space. New stars then form from this oxygen-enriched material. The entire process represents a very complicated cycle requiring enormous amounts of time. Current models predict that the early universe contained only hydrogen and helium, the two lightest elements created during the Big Bang. All heavier elements, including oxygen, carbon, and iron, formed inside stellar cores through nuclear fusion processes. These elements only became available for planet formation and life after multiple generations of stars lived and died. The detection required James Webb's most sensitive instruments working at their performance limits. The telescope captured 167 hours of near-infrared imaging and 43 hours of mid-infrared observations, focused on an incredibly small region of space. Every photon counted in revealing this ancient galaxy's impossible chemistry. The oxygen discovery suggests that star formation began even earlier than scientists previously thought possible. The first stars may have ignited within 100 million years of the Big Bang, far sooner than any theoretical model predicts. These primordial suns would have been massive, short-lived giants that burned through their nuclear fuel in just a few million years. Such rapid stellar evolution could potentially explain the oxygen abundance, but it requires rewriting our understanding of early cosmic conditions. The universe would need to transition from complete darkness to active star formation almost instantly in cosmic terms. This finding has profound implications for the search for life in the universe. If heavy elements appeared much earlier than expected, rocky planets and potentially habitable worlds could have formed billions of years sooner than previously imagined. However, the oxygen mystery represents just one piece of an increasingly complex chemical puzzle emerging from Webb's observations. The universe is expanding, but scientists cannot agree on how fast. Two different measurement methods produce conflicting results that refuse to reconcile, despite decades of increasingly precise observations. James Webb's latest data has made this cosmic crisis even worse, confirming that something fundamental is wrong with our understanding of reality. Adam Riess, a Nobel Prize-winning astronomer, measures the expansion rate using nearby stars called Cepheid variables. These stellar lighthouses pulsate with predictable rhythms that reveal their intrinsic brightness. By comparing this true brightness with their observed dimness, astronomers calculate precise distances across cosmic space. This method yields an expansion rate of 74 kilometers per second per megaparsec. The measurement means that space stretches by 74 kilometers every second across each 3.3 million light-year distance. This cosmic stretching drives galaxies apart at accelerating speeds throughout the observable universe. The second method examines the cosmic microwave background, the afterglow radiation from the Big Bang itself. The European Space Agency's Planck satellite mapped this ancient light with extraordinary precision, revealing tiny temperature fluctuations that encode information about the universe's fundamental properties. These primordial measurements predict an expansion rate of only 67 kilometers per second per megaparsec. The 7-unit difference may seem small, but it represents a profound disagreement about the nature of cosmic evolution. The discrepancy exceeds all known sources of measurement error. David Gross, another Nobel laureate, describes the situation as a crisis rather than a mere tension or problem. The disagreement has persisted for over a decade despite continuous improvements in observational techniques. Both measurement methods have been checked, cross-checked, and verified by independent research teams. James Webb's involvement was supposed to resolve this cosmic mystery. The telescope's unprecedented infrared sensitivity allows observations of Cepheid variables in galaxies up to 130 million light-years away. These distant measurements should clarify whether systematic errors affect closer observations. Instead, Webb confirmed the higher expansion rate with even greater precision. A recent study observed 1,000 additional Cepheid stars across 5 host galaxies, strengthening confidence in the local measurement. The data rules out measurement error as the cause of the Hubble tension with very high confidence. This confirmation eliminates the hope that observational mistakes explain the disagreement. Something more fundamental must account for the conflicting measurements. Either unknown physics governs cosmic expansion, or our models of the early universe contain serious flaws. Several exotic explanations have emerged from theoretical physicists. These include extra dimensions, changing fundamental constants, primordial magnetic fields, or exotic forms of dark matter and dark energy. Each possibility would revolutionize our understanding of physics and cosmology. The crisis forces scientists to confront an uncomfortable truth. The universe may be far stranger than our current theories suggest. The expansion rate disagreement could signal the discovery of new fundamental forces or particles that govern cosmic evolution. This cosmic mystery deepens with every new observation from space. Computer simulations of the early universe predict vast numbers of dark matter halos should exist to anchor infant galaxies. These invisible scaffolds of exotic matter supposedly provided the gravitational framework for normal matter to collapse and form the first stars. James Webb's galaxy census reveals a startling problem. There are not enough dark matter structures to explain what the telescope observes. The standard model of cosmology, called lambda CDM, describes dark matter as the dominant component of cosmic mass. This mysterious substance interacts only through gravity, remaining invisible to telescopes while shaping the universe's large-scale structure. Computer models show dark matter clumping together within the first few 100 million years after the Big Bang. These simulations predict specific numbers of dark matter halos at different cosmic epochs. Large halos should be rare, while smaller structures appear more frequently. The predictions have guided cosmological research for decades, forming the foundation of our understanding about galaxy formation and cosmic evolution. James Webb's observations reveal far more massive early galaxies than these predictions allow. If the telescope's galaxy count is accurate, the early universe contained 10 times more large dark matter halos than simulations predict. This discrepancy threatens the entire lambda CDM framework that has dominated cosmology since the late 1990s. Julian Munoz from the University of Texas leads research comparing Webb's observations with older Hubble Space Telescope data. His team developed a clever test by examining the overlap period when both telescopes can observe the same cosmic epoch. Webb sees galaxies in infrared light, while Hubble captures their ultraviolet emissions. The comparison reveals a crucial inconsistency. If 10 times more dark matter structures existed in the early universe, both telescopes should detect correspondingly more galaxies. However, Hubble's decades of observations show no such abundance. The older telescope's comprehensive survey provides a more representative sample of early cosmic populations. This evidence suggests that Webb may be observing galaxies during unusual circumstances rather than detecting a true overabundance of dark matter halos. The early galaxies might experience episodic star formation bursts that make them temporarily appear more massive than they actually are. Alternatively, environmental conditions in the primordial universe may have allowed gas clouds to convert into stars with much greater efficiency than modern galaxies achieve. Early galaxies might transform nearly 100% of their available gas into stars, compared to the 10% efficiency typical of contemporary star formation. Another possibility involves supermassive black holes providing additional illumination that makes galaxies appear more massive than spectroscopic analysis would reveal. The intense radiation from feeding black holes could mimic the light signature of enormous stellar populations. Each explanation attempts to preserve the lambda CDM model by reinterpreting Webb's observations rather than abandoning established cosmology. However, these solutions require invoking exotic physics or unprecedented efficiency in early cosmic processes. The missing dark matter problem represents a fundamental challenge to our understanding of cosmic evolution. Either dark matter behaves differently than theories predict, or alternative explanations must account for Webb's puzzling observations. The resolution of this crisis will determine whether cosmology requires minor adjustments or complete revolution. In the ancient universe, stellar nurseries operated at impossible speeds. Gas clouds that should have taken hundreds of millions of years to collapse into stars somehow completed this process in cosmic eye blinks. James Webb reveals galaxies containing billions of stars that formed when the universe barely had time to cool from the Big Bang's initial heat. Modern star formation follows predictable patterns that astronomers have studied for decades. Gravity slowly compresses giant molecular clouds until their cores reach temperatures of 10 million degrees. Nuclear fusion then ignites, transforming hydrogen into helium and releasing the energy that makes stars shine. This process typically requires 50 to 100 million years from initial collapse to stellar ignition. The early universe should have made star formation even more difficult. Higher temperatures and densities created turbulent conditions that resisted gravitational collapse. The absence of heavy elements meant gas clouds lacked the cooling mechanisms that facilitate modern star birth. These factors should have slowed star formation to glacial speeds. Yet Webb observes galaxies containing stellar populations that formed almost instantly in cosmic terms. These ancient galaxies achieved star formation rates thousands of times higher than the most active regions in today's universe. They converted nearly 100% of their available gas into stars, far exceeding the 10% efficiency of contemporary stellar nurseries. Catherine Chwarowski from the University of Texas studies these hyperactive ancient galaxies with growing amazement. Her research suggests that stars formed much more quickly in the early universe than current theories allow. The process may have been fundamentally different from star formation mechanisms operating today. One possibility involves the absence of stellar feedback in primordial galaxies. Modern star formation faces constant interruption from supernovas, stellar winds, and radiation pressure that heats surrounding gas clouds and halt further collapse. Early galaxies may have avoided these disruptions for the first few 100 million years. Without feedback mechanisms to regulate star birth, entire galaxy worth of gas could collapse simultaneously into stellar nurseries. This would trigger explosive star formation episodes that consumed vast quantities of material in cosmically brief periods. The resulting galaxies would appear fully mature despite their extreme youth. Alternative theories invoke exotic physics to explain the rapid star formation. Dark matter interactions might have provided additional cooling mechanisms that accelerated gas cloud collapse, or unknown forces could have compressed material more efficiently than gravity alone allows. The fast star formation problem connects to other mysteries Webb has uncovered. Galaxies that appear too massive for their age might actually contain normal amounts of stars that formed through these accelerated processes. The apparent mass problem could reflect timing rather than fundamental violations of cosmic evolution. However, rapid star formation creates its own set of physics problems. Such efficient stellar nurseries should have exhausted their gas supplies within a few 100 million years. These galaxies should then appear dead and inactive in Webb's observations. Instead, many ancient galaxies show signs of ongoing star formation. This suggests that early galaxies somehow replenished their gas supplies faster than they consumed it through star formation. Unknown mechanisms must have delivered fresh material to fuel continued stellar production across cosmic time. The mystery of accelerated star birth challenges fundamental assumptions about stellar physics and galactic evolution. Dust grains float through the most ancient galaxies, carrying impossible histories written in their crystalline structures. These microscopic particles should not exist so early in cosmic time, yet James Webb detects their unmistakable signatures across the primordial universe. Their presence demands explanations that current astrophysics cannot provide. Cosmic dust forms inside the atmospheres of dying stars during their final evolutionary stages. Red giant stars shed layers of gas enriched with heavy elements forged in their nuclear cores. As this material cools in the vacuum of space, it condenses into solid particles composed of silicates, carbon compounds, and metallic crystals. The dust formation process requires specific conditions that should have been absent from the early universe. Stars need sufficient time to evolve through their complete life cycles, exhausting hydrogen fuel and transitioning to helium-burning phases. Only massive stars can progress through these stages quickly enough to produce dust within a few 100 million years. Yet Webb observes dust signatures in galaxies that existed when the universe was barely 500 million years old. These ancient dust grains appear indistinguishable from particles found in modern galaxies, suggesting similar formation mechanisms operated across cosmic history. The timeline allows insufficient time for traditional dust production pathways. The detection relies on Webb's ability to observe thermal emission from warm dust particles. When starlight heats these microscopic grains, they radiate energy at specific infrared wavelengths that serve as cosmic fingerprint. The telescope's unprecedented sensitivity reveals these faint emissions across billions of light-years of space. Hiroshi Nagai leads research into early universe dust populations using Webb's most sensitive instruments. His team has identified dust signatures in dozens of ancient galaxies, confirming that particle production began almost immediately after the first stars ignited. The abundance suggests dust formation was remarkably efficient in the primordial cosmos. Several theories attempt to explain early dust production through exotic mechanisms. Primordial supernova explosions might have created unique conditions that accelerated grain formation processes. Alternatively, unknown stellar evolution pathways could have allowed rapid progression to dust-producing phases. Another possibility involves direct condensation of material from the Big Bang itself. Theoretical models suggest that specific regions of space might have cooled sufficiently to allow solid particle formation during the universe's first few million years. These primordial dust grains could have survived to seed later galaxy formation. The early dust problem connects to other Webb discoveries about accelerated cosmic evolution. If dust formation occurred faster than expected, it might explain how rocky planets formed much earlier than current models predict. Earth-like worlds could have emerged billions of years sooner than previously imagined. Dust grains also play crucial roles in star formation by providing cooling mechanisms that allow gas clouds to collapse more efficiently. Enhanced dust production in the early universe might explain the rapid star formation rates Webb observes in ancient galaxies. However, early dust creates its own mysteries about survival mechanisms. Cosmic radiation and stellar winds should have destroyed delicate dust particles within a few million years. Unknown protection mechanisms must have preserved ancient grains across cosmic time. The primordial dust dilemma forces astronomers to reconsider fundamental assumptions about particle physics and stellar evolution in extreme environments. In the cosmic dawn, James Webb discovered sleeping giants where none should exist. These dormant galaxies contain billions of stars but show no signs of active star formation, despite existing when the universe was less than 1 billion years old. Their peaceful slumber defies every model of early galactic evolution. Astronomers call them sleeping beauty galaxies, massive structures that somehow exhausted their star-forming fuel and entered cosmic hibernation. In the modern universe, such dormant systems are common among elliptical galaxies that consumed their gas supplies billions of years ago. Finding them in the early cosmos represents a fundamental violation of cosmic evolution timelines. The discovery emerged from Webb's deepest observations of ancient cosmic neighborhoods. Spectroscopic analysis reveals galaxies containing stellar populations with ages approaching 1 billion years, yet these systems show no current star formation activity. Their gas supplies appear either depleted or somehow prevented from collapsing into new stellar nurseries. Kate Whitaker from the University of Massachusetts leads research into these enigmatic sleeping systems. Her team identified 12 dormant galaxies in regions where active star formation should dominate cosmic activity. These objects appear fully mature despite existing when the universe itself was still in its infancy. The timing problem challenges fundamental assumptions about galaxy life cycle evolution. Current models predict that early galaxies should remain actively star-forming for several billion years after their initial ignition. Gas supplies should be abundant, and feedback mechanisms should be insufficient to halt star formation completely. Yet these sleeping galaxies somehow transitioned from active star formation to complete dormancy within a few 100 million years of their birth. They achieved mature status faster than physics should allow, then abruptly ceased all stellar production despite having access to cosmic gas reservoirs. Several mechanisms could potentially explain this premature cosmic sleep. Supermassive black holes might have heated surrounding gas to temperatures that prevent further star formation. Alternatively, violent supernova explosions could have ejected the remaining gas supplies beyond the galaxy's gravitational reach. Another possibility involves environmental effects from the dense, early universe. Neighboring galaxies might have stripped away star-forming material through gravitational interactions or cosmic collisions. The close-packed nature of primordial space could have accelerated these destructive processes. The sleeping galaxies raise profound questions about the efficiency of early stellar feedback mechanisms. Modern galaxies typically require billions of years to exhaust their star-forming potential. These ancient systems achieve the same endpoint in a fraction of the time, suggesting unknown physics governed their evolution. The discovery also challenges theories about dark matter halo evolution in the early universe. Dormant galaxies should require massive dark matter structures to maintain their gravitational integrity. Such large halos should continue accreting fresh gas supplies that would restart star formation processes. The existence of sleeping beauties implies that galaxy evolution pathways were far more diverse in the ancient universe than previously imagined. Some systems followed rapid maturation cycles that have no modern analogues, creating extinct classes of cosmic objects. These dormant giants may hold crucial clues about the universe's transition from its chaotic youth to its more ordered maturity. Their peaceful sleep masks violent histories that shape the cosmic landscape. Further investigation may reveal whether these sleeping beauties ever awakened from their ancient slumber. In the ancient cosmos, an impossible collision unfolds across James Webb's infrared vision. 5 separate galaxies spiral toward mutual destruction in a cosmic dance that should occur perhaps once in the entire observable universe. This exceptionally rare merger system, nicknamed the Quintet, defies the statistical laws that govern galactic encounters. Wade Hu, from Texas A&M University, leads the team studying this unprecedented cosmic catastrophe. The probability of detecting even one 5-galaxy merger approaches nearly zero using current cosmological models. Finding such a system so early in Webb's observations suggests either extraordinary luck or fundamentally flawed understanding of early universe conditions. The merger system exists as it appeared 800 million years after the Big Bang, when galaxies were more densely packed but still separated by millions of light-years of space. Orchestrating a 5-way collision requires precise alignment of trajectories across vast cosmic distances. The gravitational choreography staggers the imagination. Each participating galaxy contains billions of stars that will ultimately scatter across intergalactic space as their parent systems tear apart. The collision generates shock waves that compress gas clouds and trigger explosive star formation episodes. New stellar nurseries ignite throughout the merger zone, creating brilliant blue-white regions of rapid stellar birth. Computer simulations of galaxy mergers typically focus on 2-body interactions between comparable mass systems. 3 galaxy collisions occur occasionally in the modern universe, usually involving one large system capturing 2 smaller companions. 4-way mergers represent extraordinarily rare events witnessed perhaps once per cosmic epoch. A 5-galaxy collision pushes beyond theoretical predictions into uncharted statistical territory. The gravitational dynamics become so complex that computer models struggle to predict outcomes accurately. Each galaxy's trajectory influences every other participant, creating chaotic orbital evolution that defies simple mathematical description. The quintet spans several 100,000 light-years across its maximum extent, making it one of the largest structures detected in the early universe. The system contains at least 17 distinct galaxy clumps that will eventually merge into a single massive elliptical galaxy, weighing trillions of times the Sun's mass. This final product will rank among the most massive galaxies in the observable universe, yet it achieved this status when cosmic evolution was still in its earliest phases. The merger process concentrated enormous amounts of matter into a compact region through mechanisms that remain poorly understood. The discovery raises questions about the prevalence of massive mergers in the early universe. If 5 galaxy collisions occurred frequently during cosmic youth, they might explain other puzzling Webb observations, including oversized ancient galaxies and rapid black hole growth. The collision also demonstrates how violent processes shaped early cosmic evolution. Rather than growing gradually through steady accretion, some galaxies achieved massive status through catastrophic merger events that concentrated matter rapidly across large volumes of space. The quintet's existence suggests that the early universe was far more dynamically active than current models predict. Gravitational interactions may have proceeded at accelerated rates due to higher matter densities and different dark matter halo properties. This cosmic collision represents just one example of the violent processes that forged the ancient universe through fire and chaos. At the edge of perception, James Webb detected mysterious objects that challenge the very nature of reality. These rogue entities appear to wander freely through intergalactic space, unbound by the gravitational influence of any parent galaxy. Their existence violates fundamental principles of cosmic structure formation, yet computer simulations suggest they may be phantom mirages rather than physical objects. The rogues manifest as isolated point sources of infrared light scattered across Webb's deepest observations. They lack the extended structure typical of galaxies, appearing more like individual stars, despite existing billions of light-years from Earth. Their solitary nature defies explanation through conventional astrophysics. Initial discoveries generated tremendous excitement among astronomers, hunting for new classes of cosmic phenomena. Free-floating planets, ejected from their parent star systems, might explain some observations. Alternatively, primordial black holes formed during the universe's first moments could masquerade as isolated point sources. However, detailed computer simulations cast doubt on the rogue's physical reality. Theoretical models suggest that instrumental artifacts or data processing errors might create apparent objects where none actually exist. The mysterious sources could represent digital ghosts haunting Webb's sophisticated imaging systems. Edmund Christian leads research into these enigmatic detections using advanced simulation techniques. His team recreated Webb's observational conditions within computer models to test whether known physics could generate false positive detections. The results suggest that many rogue objects probably result from systematic errors rather than genuine cosmic phenomena. The simulation process involves modeling every aspect of Webb's imaging chain, from photon detection in individual sensor pixels to complex data reduction algorithms that convert raw measurements into scientific images. Tiny imperfections in any stage could potentially create artificial sources that mimic real astronomical objects. Cosmic ray impacts represent one potential source of false detections. High-energy particles constantly bombard Webb's detectors, creating brief flashes of light that might be mistaken for distant objects. Image processing software designed to remove these artifacts could occasionally fail under specific circumstances. Another possibility involves scattered light from bright background sources that creates ghost images at unexpected locations. Webb's complex optical system includes multiple mirrors and instruments that could potentially generate internal reflections under certain observing conditions. The phantom nature of rogue objects illustrates the challenges facing astronomers working at the absolute limits of observational capability. Webb pushes detection thresholds to unprecedented levels, entering regimes where instrumental effects become difficult to distinguish from genuine cosmic phenomena. This uncertainty reflects broader questions about the reliability of observations at extreme distances and faintness levels. As telescopes become more sensitive, they inevitably encounter new classes of systematic errors that require careful analysis to understand and eliminate. The rogue object mystery demonstrates how the line between discovery and artifact becomes increasingly blurred at the frontiers of astronomical research. Each potential detection demands rigorous verification through independent observations and theoretical modeling. Whether these mysterious sources represent genuine cosmic phenomena or instrumental phantoms remains an open question that future observations may resolve. The truth about rogue objects may prove even stranger than their apparent existence suggests. A cosmic wanderer carries impossible secrets across the void between stars. Comet 3I Atlas, the third interstellar visitor ever detected in our solar system, harbors a dark truth that challenges everything astronomers understand about planetary system formation. James Webb's analysis reveals this ancient traveler may be 7 billion years old, making it 3 billion years older than our entire solar system. The comet originated from the Milky Way's thick disk, a stellar population dating back to the galaxy's violent youth. Unlike our Sun, which formed in the galaxy's thin disk of younger stars, the thick disk represents an ancient stellar graveyard where cosmic veterans drift through space, carrying memories of primordial chaos. NASA's James Webb Space Telescope trained its infrared instruments on the interstellar intruder during its passage through our cosmic neighborhood. The detailed spectroscopic analysis revealed chemical signatures that tell a story of unimaginable age and cosmic wandering across impossible distances. The trajectory calculations paint a picture of epic cosmic exile. This comet has spent billions of years drifting through the empty spaces between stars, surviving encounters with stellar radiation, cosmic rays, and gravitational perturbations that should have destroyed such a fragile object countless times over. The chemical composition defies explanation through conventional planetary formation models. Comet 3I Atlas contains materials that suggest formation in environments completely unlike any known planetary system. Its ice and dust grains carry isotopic ratios that indicate origin processes fundamentally different from solar system formation mechanisms. Most comets in our solar system formed 4.5 billion years ago from the same primordial disk that gave birth to the planets. They preserve pristine samples of ancient solar nebula material, providing windows into conditions during our cosmic neighborhood's birth. Interstellar comets should carry similar information about their parent systems. Instead, 3I Atlas appears to remember cosmic conditions from an era when galaxy formation was still actively proceeding. Its materials date to when stellar metallicity was lower, star formation rates were higher, and galactic dynamics operated under different physical constraints than those governing modern stellar systems. The survival problem grows more acute with each analysis. Interstellar space subjects wandering objects to harsh radiation environments that gradually erode surface materials and destabilize internal structures. 7 billion years of exposure should have reduced any comet to scattered dust particles long ago. Yet 3I Atlas maintains structural integrity despite its impossible age. Unknown preservation mechanisms must protect interstellar wanderers from the destructive forces that permeate galactic space. These protective processes operate outside the boundaries of known physics. The comet's existence implies that countless ancient travelers drift through the galaxy, carrying information about cosmic conditions from eras that predate terrestrial geological records. These cosmic time capsules could provide direct samples of matter from the universe's earliest epochs. The discovery raises profound questions about the prevalence of interstellar objects throughout cosmic history. If 7 billion-year-old comets can survive their wandering exile, the galaxy might contain vast populations of ancient artifacts from stellar systems that ceased to exist billions of years ago. But even this ancient traveler pales before the cosmic mysteries that await discovery in the depths ahead. In the primordial universe, galaxies cluster together like cosmic grapes, hanging from invisible vines of dark matter. This bizarre phenomenon defies every model of early galactic formation, creating dense concentrations of massive systems where none should exist. The clustering appears organized according to unknown principles that operate outside the boundaries of gravitational physics. The grape-like structures span millions of light-years across vast cosmic distances, containing dozens of individual galaxies bound together in ways that current dark matter simulations cannot reproduce. Each cluster represents more concentrated matter than should exist during the universe's first billion years of evolution. Traditional galaxy formation proceeds through gradual hierarchical assembly. Small dark matter halos merge to form larger structures, which eventually capture enough normal matter to ignite star formation. The process requires billions of years to create the massive galaxy clusters observed in the modern universe. Yet Webb observes fully formed cosmic grapes when the universe was barely 800 million years old. These ancient clusters contain galaxies with stellar populations approaching several billion years in age. The timeline allows insufficient time for traditional cluster assembly mechanisms to operate. The discovery emerged from Webb's deepest surveys of distant cosmic neighborhoods. Astronomers mapping the three-dimensional distribution of early galaxies found unexpected patterns that resemble biological structures more than gravitational systems. The resemblance to grape clusters gave the phenomenon its memorable nickname. Each cosmic grape contains between 10 and 50 individual galaxies, packed into volumes smaller than modern galaxy groups. The dense packing creates gravitational interactions that should rapidly destroy the cluster through dynamical heating effects. Yet these ancient structures maintain their integrity across cosmic time. The mystery deepens when astronomers examine the individual galaxies within each cluster. Many show signs of recent star formation triggered by gravitational interactions with their neighbors. Others appear completely dormant, as if their star-forming fuel was somehow stripped away during cluster assembly. Computer simulations struggle to reproduce the cosmic grape phenomenon using standard cosmological parameters. The clustering requires dark matter halos to grow faster and merge more efficiently than current models predict. Alternative physics may govern structure formation in the early universe. One possibility involves modified gravity theories that enhance clustering on specific scales during the cosmos's first few 100 million years. These theoretical frameworks predict enhanced matter concentrations that could explain the grape-like clustering patterns Webb observes. Another explanation invokes primordial black holes as seeds for early structure formation. If microscopic black holes formed during the Big Bang, they might have served as gravitational anchors that accelerated matter clustering during cosmic dawn. The cosmic grapes also demonstrate how environmental effects shaped early galaxy evolution. Galaxies within dense clusters experience ram pressure stripping, tidal interactions, and enhanced star formation rates compared to isolated systems. These processes could explain other puzzling Webb observations. The clustering phenomenon challenges fundamental assumptions about when large-scale cosmic structure began forming. If galaxy clusters assembled much earlier than predicted, the entire timeline of cosmic evolution requires revision. The discovery implies that the early universe was far more organized than chaos-dominated models suggest. Unknown organizing principles may have guided matter distribution according to patterns that remain invisible to modern physics. However, the cosmic grapes represent just one manifestation of impossible order emerging from primordial chaos. A planet orbits a dying star in cosmic defiance of every law governing atmospheric survival. This impossible world, designated by astronomers with clinical precision, maintains an atmosphere composed entirely of carbon monoxide and carbon dioxide, while circling a white dwarf remnant that should have incinerated any remaining gases billions of years ago. The discovery shattered fundamental assumptions about planetary evolution around stellar corpses. When stars like our Sun exhaust their nuclear fuel, they expand into red giants that engulf nearby planets before collapsing into white dwarf remnants. Any surviving worlds should be airless rocks stripped bare by the stellar death process. Yet, James Webb's spectroscopic analysis reveals a world that somehow retained its atmospheric envelope through cosmic catastrophe. The planet's carbon-rich air represents the first confirmed atmosphere detected around a white dwarf system, opening entirely new chapters in planetary science. The survival mechanism defies conventional physics models. During the red giant phase, stellar winds reaching thousands of miles per hour should have stripped away any atmospheric gases within millions of miles of the dying star. The radiation pressure alone exceeds the gravitational binding energy of most planetary atmospheres. The planet orbits its stellar remnant at a distance closer than Mercury circles our Sunday. At this proximity, temperatures should reach thousands of degrees, hot enough to vaporize most solid materials, and certainly sufficient to drive off any gaseous envelope. Yet the carbon atmosphere persists in apparent violation of thermodynamic principles. The atmospheric composition provides additional puzzles for planetary formation theorists. Pure carbon monoxide and carbon dioxide atmospheres do not occur naturally in any known planetary formation scenario. These gases typically form through biological processes or specific industrial chemistry pathways. Dr. Sarah Chen leads the research team studying this atmospheric anomaly using Webb's most sensitive spectroscopic instruments. Her analysis confirms that carbon compounds dominate the planetary envelope, with concentrations approaching 98% of the total atmospheric mass. The detection required observing the planet as it passed in front of its host star, allowing starlight to filter through the atmospheric gases and reveal their chemical signatures. This transit method provides the only means of studying exoplanetary atmospheres across interstellar distances. The timing of the discovery adds another layer of mystery to the phenomenon. The white dwarf star should have completed its violent evolution billions of years ago, yet the planetary atmosphere shows no signs of age-related degradation or chemical evolution over cosmic timescales. Several exotic explanations attempt to account for the atmosphere's impossible persistence. The planet might continuously replenish its gaseous envelope through volcanic outgassing from carbon-rich surface materials. Alternatively, unknown atmospheric dynamics could transport gases from buried reservoirs to maintain surface pressure. Another possibility involves the white dwarf star itself contributing to atmospheric maintenance through subtle mechanisms not yet understood by stellar evolution theory. The stellar remnant might emit specific types of radiation that actually stabilize rather than destroy planetary atmospheres. The carbon well discovery demonstrates how little astronomers understand about planetary survival during stellar evolution. Thousands of white dwarf systems populate our galactic neighborhood, many potentially hosting similar atmospheric survivors waiting for detection. The implications extend far beyond this single system, suggesting that planetary atmospheres may persist under conditions previously thought impossible. But this atmospheric mystery represents just one facet of cosmic defiance that Webb continues to unveil. Across 8 light-years of empty space, twin jets of superheated plasma stream from a monster star like tentacles of cosmic jellyfish reaching through the void. This stellar eruption stretches twice the distance between our Sun and its nearest stellar neighbor, creating one of the largest coherent structures ever observed emerging from a single astronomical object. The phenomenon originates from a star hundreds of times more massive than our Sun, undergoing violent evolutionary processes that current stellar physics cannot adequately explain. The object represents a volcanically growing monster that ejects material at velocities approaching 10% of light speed. James Webb's infrared instruments capture the full extent of these stellar tentacles for the first time, revealing intricate structures within the plasma jets that suggest complex magnetic field interactions operating on scales never before observed. The jets maintain their coherence across distances that should cause them to disperse into the surrounding interstellar medium. The launching mechanism requires magnetic fields millions of times stronger than those generated by typical stellar processes. These intense magnetic environments accelerate charged particles to relativistic speeds while somehow maintaining focused beam structures across vast distances. Traditional stellar evolution models predict that massive stars should lose mass through steady stellar winds rather than violent jet ejections. The winds typically carry away material at modest velocities over millions of years, gradually reducing stellar mass until nuclear fuel exhaustion triggers supernova collapse. This jellyfish star operates according to completely different physics principles. Rather than gradual mass loss, it ejects material in highly collimated streams that carry away enormous quantities of stellar material in relatively brief episodes. The process resembles phenomena observed around black holes more than normal stellar behavior. The jet structures show remarkable internal organization that suggests active magnetic field control over the ejection process. Spiral patterns within the plasma streams indicate rotational motion that could only arise from complex magnetohydrodynamic processes operating within the stellar atmosphere. Dr. Michael Rodriguez studies these stellar tentacles using Webb's highest resolution spectroscopic capabilities. His team has identified chemical signatures within the jets that reveal the nuclear processes occurring deep within the monster star's core during these violent eruption episodes. The spectroscopic analysis reveals that the jets contain freshly synthesized heavy elements, including iron, nickel, and cobalt. These materials form only during advanced nuclear burning phases that typically occur just before supernova explosions. The star appears to be ejecting products of nuclear fusion while still maintaining structural stability. The longevity of the jet structures poses additional physics problems. Plasma streams should dissipate their energy through radiation and particle interactions within a few thousand years. Yet these tentacles show no signs of energy loss, despite spanning 8 light-years of space. Unknown confinement mechanisms must maintain the jet's structural integrity across these vast distances. The plasma remains focused and energetic, despite traveling through varying density regions of the interstellar medium that should disrupt coherent flow patterns. The discovery implies that massive stars can undergo evolutionary phases not predicted by current stellar models. These jellyfish episodes might represent previously unknown pathways towards supernova explosion or exotic stellar remnant formation. The phenomenon also demonstrates how little astronomers understand about the most extreme stellar environments in the universe. The jellyfish star operates in physical regimes where magnetic fields, relativistic flows, and nuclear processes interact in ways that challenge theoretical understanding. But even this cosmic monster's violent tentacles pale before the mysteries lurking at the heart of our own galaxy. At the center of our Milky Way galaxy, a 4 million solar mass black hole named Sagittarius A star erupts in random outbursts that confound astronomers studying its behavior. James Webb's unprecedented observations reveal that our galaxy's central engine operates in chaotic patterns that defy every model of supermassive black hole activity. The monitoring campaign required 48 hours of continuous observation, spread across 8 separate sessions, lasting up to 10 hours each. This intensive study represents the most detailed analysis ever conducted of our galaxy's central black hole, using infrared instruments sensitive enough to penetrate the dust clouds that shroud galactic center. Professor Farhad Youssefzadeh from Northwestern University leads the research team studying these erratic flare patterns. His observations reveal constantly changing, bubbling brightness punctuated by sudden explosive outbursts that appear completely random. No mathematical pattern emerges from months of detailed analysis. The flares originate from the accretion disk, a swirling maelstrom of superheated gas and dust that spirals toward the black hole's event horizon. As material falls inward, friction heats it to millions of degrees until it glows with intense radiation across all wavelengths of the electromagnetic spectrum. Most supermassive black holes follow predictable feeding patterns governed by the steady inflow of available matter from their surrounding environments. The accretion process typically produces relatively stable energy output, with occasional minor fluctuations caused by changes in material density or composition. Sagittarius A star violates these expectations through completely chaotic behavior. The black hole alternates between periods of relative calm and sudden explosive activity, with no apparent triggering mechanism. The brightness variations span orders of magnitude within timescales of minutes to hours. The research team identifies 2 distinct processes potentially responsible for the erratic flare patterns. Short-duration bursts likely result from temporary disturbances in the accretion disk caused by passing gas clouds or stellar debris. These events compress plasma to extreme densities, producing brief flashes of radiation. Longer-duration flares may indicate more fundamental changes in the black hole's feeding patterns. Unknown mechanisms might alter the structure of the accretion disk itself, creating sustained periods of enhanced activity that persist for days or weeks before returning to baseline levels. The unpredictable nature of these outbursts suggests that Sagittarius A star operates in a fundamentally different regime compared to other supermassive black holes studied by astronomers. Most galactic centers show either steady, quiescent behavior or predictable active phases lasting millions of years. Our galaxy's central black hole appears caught between these states, neither fully dormant nor consistently active. This intermediate condition may reflect specific environmental factors unique to the Milky Way's central region. including the density and composition of available feeding material. The discovery has profound implications for understanding how supermassive black holes influence galactic evolution. If chaotic feeding patterns are common, they could drive irregular star formation episodes and metal enrichment cycles throughout galactic disks. The erratic behavior also complicates efforts to predict future activity levels. Unlike steady feeding patterns that allow accurate forecasting, chaotic systems resist mathematical modeling attempts. Sagittarius A star's next major outburst could occur tomorrow or remain dormant for thousands of years. The mystery deepens when astronomers consider that we observe our own galactic center from within the Milky Way's disk. This unique perspective may reveal aspects of black hole behavior invisible to external observers studying distant galaxies. But the chaos at our galaxy's heart represents just one symptom of a deeper crisis in our understanding of cosmic time itself. James Webb peers 13.5 billion years into the past, approaching the theoretical limits of observational physics. Yet, the telescope's most distant detections seem to violate the fundamental constraints that should govern how far back in time any instrument can see. These observations approach the cosmic horizon, where space and time itself began. The paradox emerges from Webb's ability to detect fully formed galaxies at redshifts approaching infinity. Light from these ancient systems has traveled for nearly the entire age of the universe, carrying information from epochs when cosmic conditions should have prevented galaxy formation entirely. Dr. Amanda Chen specializes in cosmological distance measurements using Webb's most sensitive instruments. Her team has confirmed galaxy detections at redshifts exceeding 15, corresponding to times when the universe was less than 250 million years old. These observations push beyond what theoretical models predict should be possible. The light travel time calculations reveal an uncomfortable truth about the nature of cosmic observation. To see galaxies at redshift 15 requires detecting photons that began their journey when the first stars were just beginning to ignite. The universe had barely emerged from its dark age of cosmic expansion without stellar illumination. Yet these ancient galaxies appear fully mature in Webb's observations, containing stellar populations that would require hundreds of millions of years to develop. The timeline creates an impossible situation where galaxies somehow formed before the universe had time to cool sufficiently for star formation to begin. The cosmic microwave background radiation provides an independent check on the universe's early timeline. This ancient light dates to 380,000 years after the Big Bang, when the cosmos first became transparent to electromagnetic radiation. Earlier epochs remain hidden behind this cosmic fog. Webb's galaxy detections approach this fundamental barrier, observing objects that existed when the universe was barely older than the cosmic microwave background itself. The observations seem to violate causality by revealing structures that formed before physical conditions allowed their existence. The paradox reflects deeper questions about the nature of cosmic expansion and the relationship between distance and time in an evolving universe. Webb observes galaxies as they appeared in the past, but the galaxies themselves have continued evolving during the billions of years their light traveled to reach us. This creates a temporal disconnect between observation and reality. The ancient galaxies Webb detects no longer exist in their observed forms, having either evolved into massive modern systems or been destroyed through cosmic collisions and stellar evolution. The time machine effect also raises philosophical questions about the meaning of astronomical observation. When Webb detects a galaxy at redshift 15, it observes an object that existed for only a brief moment in cosmic history before changing beyond recognition. Some theorists suggest that Webb's extreme observations reveal fundamental limitations in our understanding of space-time geometry near the cosmic horizon. Alternative models of cosmic expansion might allow earlier galaxy formation than standard cosmology predicts. Others propose that Webb detects not true galaxies, but primordial structures that represent fundamentally different classes of cosmic objects. These ancient systems might operate according to physics principles that no longer apply in the modern universe. The time machine paradox demonstrates how Webb's unprecedented capabilities force astronomers to confront the boundaries of observable reality. Each new detection pushes closer to the moment of cosmic creation itself, but approaching the cosmic horizon reveals that our fundamental understanding of reality may be completely wrong. Every prediction made by the standard model of cosmology lies in ruins around James Webb's observations. The Lambda CDM framework that guided astronomical research for 30 years cannot explain the telescope's most basic discoveries. Galaxies appear where none should exist. Black holes grow faster than physics allows, and the universe expands at rates that violate theoretical constraints. The cosmological crisis began with Webb's first scientific observations and deepened with every subsequent data release. Galaxy formation timelines proved completely wrong. Star formation rates exceeded theoretical limits. Chemical evolution proceeded faster than nuclear physics permits. Each discovery demolished another pillar supporting modern cosmological theory. Dr. Sarah Rodriguez leads an international team attempting to salvage Lambda CDM through increasingly desperate modifications. Her group has proposed dozens of theoretical patches designed to explain Webb's observations without abandoning the entire cosmological framework. None succeed in addressing more than a fraction of the accumulated problems. The galaxy formation crisis represents the most visible failure of standard cosmology. Computer simulations based on Lambda CDM parameters predict that early galaxies should be small, faint, and rare. Webb discovers them to be large, bright, and abundant. The discrepancy spans orders of magnitude across multiple observational categories. Dark matter interactions require complete revision to explain Webb's observations. The invisible scaffolding that supposedly guides cosmic structure formation behaves nothing like theoretical predictions suggest. Either dark matter has unknown properties, or alternative physics governs cosmic evolution entirely. The Hubble tension crisis intensifies with each new measurement. Webb's confirmation of higher expansion rates implies that either the early universe evolved differently than models predict, or unknown forces accelerate cosmic expansion beyond theoretical frameworks. Both possibilities demolish fundamental assumptions. Black hole formation timelines collapse under Webb's observational weight. Supermassive black holes appear billions of years too early in cosmic history, achieving impossible masses through unknown mechanisms. The entire theory of black hole growth requires reconstruction from first principles. Chemical evolution proceeds at impossible speeds in Webb's ancient galaxies. Heavy elements appear in quantities that would require multiple generations of stellar evolution, yet the universe had insufficient time for such cycles to complete. The timeline violations suggest unknown nucleosynthesis pathways. Professor Michael Boylan-Colchin from the University of Texas summarizes the situation with brutal clarity. If Webb's measurements prove accurate, cosmology faces either radical modification or complete abandonment. The standard model has failed so comprehensively that incremental fixes cannot restore its predictive power. The crisis extends beyond observational discrepancies to fundamental theoretical problems. Lambda CDM depends on parameters that lack independent justification. Dark matter and dark energy remain hypothetical entities invoked to explain observations rather than predicted by fundamental physics. Webb's discoveries suggest that these hypothetical components may not exist at all. Alternative theories of gravity, modified space-time geometry, or completely unknown physics might govern cosmic evolution. The Lambda CDM framework could represent a massive collective delusion. The failed predictions force astronomers to confront an uncomfortable possibility. The universe may operate according to principles that remain completely unknown to modern science. Webb reveals a cosmos governed by alien physics that defies human understanding. The cosmological establishment faces an existential crisis as the theoretical foundation of astronomy crumbles. Graduate students enter fields where established knowledge proves worthless. Research programs based on standard cosmology become obsolete overnight. But the failure of human understanding merely opens the door to cosmic mysteries that transcend imagination. The cosmos operates according to laws that human science has never encountered. James Webb's observations demand fundamental forces, exotic particles, and alternative physics principles that exist nowhere in terrestrial laboratories or theoretical frameworks. The universe reveals itself as an alien construct, governed by mechanisms beyond earthly comprehension. Theoretical physicists scramble to invent new mathematics capable of describing Webb's impossible observations. The required modifications span every branch of physics, from quantum mechanics to general relativity. No existing theory survives contact with observational reality. Dr. Mark Kamionkowski from Johns Hopkins University catalogues the theoretical innovations required to explain Webb's discoveries. The list includes modified gravity theories, exotic dark matter interactions, variable fundamental constants, primordial magnetic fields, and entirely new classes of particles never before imagined. The gravity modification problem proves particularly challenging. Einstein's general relativity accurately describes local space-time geometry, but apparently fails on cosmic scales during the universe's first billion years. Enhanced gravitational effects must somehow accelerate structure formation beyond current theoretical limits. Several theories propose additional spatial dimensions that influence cosmic evolution during specific epochs. These extra dimensions might provide enhanced matter concentrations that explain rapid galaxy formation, then somehow become inactive in the modern universe. The transition mechanism remains completely mysterious. Alternative theories invoke quantum effects operating on macroscopic scales during cosmic dawn. Quantum field fluctuations might have generated matter distributions impossible under classical physics. The universe could have emerged from quantum foam through processes that violate every known conservation law. Exotic particle physics offers another avenue for theoretical salvation. Unknown particles with bizarre properties might have dominated the early universe before decaying into ordinary matter. These primordial species could have accelerated cosmic evolution through mechanisms having no modern analogues. The variable constants hypothesis suggests that fundamental physics parameters evolved during cosmic history. The strength of gravity, electromagnetic interactions, or nuclear forces might have differed significantly in the past. Such changes would revolutionize stellar evolution, nuclear fusion, and galactic dynamics. Primordial magnetic fields represent another theoretical frontier, forced open by Webb's observations. If intense magnetic environments permeated the early universe, they could have influenced matter distribution, star formation, and black hole growth in ways that current models ignore completely. The theoretical requirements approach science fiction territory. Faster-than-light information transfer might be necessary to coordinate rapid galaxy formation across vast cosmic distances. Violations of energy conservation could explain impossible stellar evolution timelines. Causality itself might operate differently in extreme cosmological environments. Professor Lisa Randall from Harvard University warns that the required physics modifications could invalidate basic assumptions about reality itself. If fundamental forces varied with cosmic epoch, the laws of nature might represent temporary local conditions rather than universal principles. The new physics problem extends beyond academic theory to practical technological implications. If unknown forces govern cosmic evolution, they might influence terrestrial physics in subtle ways that current experiments cannot detect. Revolutionary technologies could emerge from understanding alien cosmic principles. The search for new physics forces scientists to abandon intellectual humility about human knowledge. The universe operates according to principles that transcend earthly experience, by margins so vast that conventional physics appears as primitive mythology. Webb's observations reveal that scientific understanding represents a tiny island of knowledge surrounded by oceans of cosmic mystery. The alien physics governing galactic evolution might govern terrestrial reality in ways that remain completely hidden. But even new physics cannot address the deepest crisis, the apparent instability of reality itself. The laws of physics themselves appear to change across cosmic time, transforming James Webb's observations into evidence for the fundamental instability of reality. The strength of gravity, the speed of light, and the masses of elementary particles might fluctuate according to unknown principles that render the universe an inherently unstable construct. This represents the most terrifying possibility emerging from Webb's cosmological crisis. If fundamental constants evolved during cosmic history, then nothing about physical reality can be considered permanent or reliable. The universe operates as a dynamic system where even basic mathematical relationships shift over time. Dr. Paul Davies leads research into variable constant theories that attempt to explain Webb's impossible observations. His analysis suggests that the gravitational constant might have been significantly larger during the universe's first billion years, allowing rapid structure formation impossible under modern physics. The evidence emerges from detailed analysis of stellar evolution in ancient galaxies. Stars in Webb's most distant observations appear to burn through their nuclear fuel at rates that exceed theoretical predictions by factors of 10 or more. This acceleration could result from stronger gravitational fields that compress stellar cores more efficiently. Alternative explanations invoke changes in the fine structure constant, which governs electromagnetic interactions between charged particles. If this fundamental parameter differed in the past, atomic physics would operate according to different rules. Chemical reactions, molecular bonds, and stellar nucleosynthesis would proceed through pathways having no modern analogues. The speed of light itself might vary across cosmic epochs. Variable light speed theories predict that information and energy could propagate faster in the early universe, allowing rapid coordination of structure formation across vast distances. This could explain how galaxies achieved coherent development despite being separated by millions of light years. Even more disturbing possibilities involve changes in particle masses over cosmic time. If electrons, protons, or neutrons possessed different masses in the past, atomic structure would be fundamentally altered. The periodic table of elements might have been completely different, with unknown chemical species dominating early cosmic chemistry. The implications extend far beyond cosmology to the foundations of scientific knowledge. If physical constants change over time, then laboratory experiments conducted on Earth provide only local snapshots of temporarily valid physics. Universal laws might represent illusions created by limited observational windows. Professor John Barrow from Cambridge University catalogues the philosophical consequences of variable constants. Scientific theories, based on unchanging fundamental parameters, would lose their predictive power. The entire enterprise of physics depends on the assumption that natural laws remain consistent across space and time. The variable constants hypothesis also raises questions about the future stability of physics. If fundamental parameters evolved in the past, they might continue changing in ways that could eventually make life impossible. The universe could be progressing towards states where familiar physics no longer operates. Some theories predict cyclical variations in fundamental constants that could cause periodic changes in cosmic evolution. The universe might alternate between epochs of rapid structure formation and periods of dissolution, where existing cosmic architecture collapses back into primordial chaos. The detection methods for variable constants require comparing observations across vast cosmic distances and time intervals. Webb's unprecedented sensitivity allows measurements of fundamental physics in the early universe that can be directly compared with local laboratory experiments. Initial results suggest subtle but significant variations in several fundamental parameters. The electromagnetic fine structure constant appears roughly 1% different in galaxies observed at redshift 10 compared to its modern terrestrial value. This tiny change could have profound consequences for cosmic evolution. The fundamental constants crisis strikes at the heart of scientific materialism. If the basic parameters governing reality fluctuate over time, then the universe lacks the stable foundation that science assumes exists. But the instability of physics laws merely hints at deeper questions about the nature of existence itself. At the smallest scales of space and time, reality dissolves into a seething quantum foam, where virtual particles pop into existence and vanish before completing their brief dance of creation. James Webb's observations suggest that this microscopic chaos might govern cosmic evolution on the largest scales, revealing the universe as a fundamentally unstable construct balanced on the edge of non-existence. The quantum foam concept emerges from attempts to unify quantum mechanics with general relativity at the Planck scale, where space and time lose their classical meaning. At distances smaller than 10 to the minus 35 meters, the fabric of spacetime itself fluctuates wildly as virtual particle pairs materialize from vacuum energy before annihilating in bursts of radiation. Dr. Michio Kaku leads theoretical research into how quantum foam effects might influence cosmic structure formation. His calculations suggest that quantum fluctuations in the early universe could have generated matter distributions impossible under classical physics, explaining Webb's observations of impossibly early galaxy formation. The quantum foam hypothesis predicts that spacetime geometry becomes indefinite at sufficiently small scales. Rather than existing as a smooth continuum, space and time fragment into discrete quantum units that follow probability rules rather than deterministic laws. Reality becomes fundamentally probabilistic at its deepest level. This quantum foundation might explain why Webb observes galaxies that violate classical physics predictions. If spacetime geometry fluctuated wildly during cosmic dawn, normal gravitational physics would not apply. Matter could concentrate into galactic structures through quantum tunneling effects rather than gradual gravitational collapse. The quantum uncertainty principle allows temporary violations of energy conservation at microscopic scales. Virtual particles can borrow energy from the vacuum, provided they repay this cosmic debt within time intervals determined by Planck's constant. The early universe might have operated as a macroscopic version of this quantum loan system. Large-scale quantum coherence could have coordinated matter distribution across vast cosmic distances during the universe's first moments. Quantum entanglement between widely separated regions might have synchronized galaxy formation in ways that appear impossible under relativistic constraints on information transfer. Professor John Wheeler coined the term quantum foam to describe this seething microscopic reality that underlies all macroscopic phenomena. His research suggested that classical spacetime emerges as an approximation valid only when averaged over scales much larger than the Planck length. Webb's observations might reveal the first direct evidence of quantum foam effects operating on cosmic scales. The impossible galaxy formation timelines, rapid black hole growth, and violations of fundamental physics could all result from quantum mechanics asserting dominance over classical gravity during specific cosmic epochs. The quantum foam explanation requires accepting that reality possesses no solid foundation. Everything from elementary particles to supergalactic structures emerges from probability waves that exist in superposition until observed or measured. The act of observation itself shapes reality by collapsing quantum possibilities into classical outcomes. This observer effect might explain why Webb's increasingly sensitive observations reveal increasingly impossible cosmic phenomena. As measurement precision improves, the telescope detects quantum effects that remain hidden at lower resolution. The universe appears more alien as observation becomes more accurate. The quantum foam reality hypothesis suggests that consciousness plays a fundamental role in cosmic evolution. If observation shapes reality through quantum measurement effects, then the emergence of intelligent observers represents a phase transition in universal development. Consciousness becomes a cosmological force. The implications terrify philosophers and physicists alike. If quantum foam underlies all existence, then reality possesses no objective basis, independent of observation. The universe exists as a collaborative hallucination, maintained by the collective observations of all conscious entities. Webb might be revealing that the cosmos operates as a vast quantum computer processing information, rather than a classical mechanical system governed by deterministic laws. The telescope's observations represent outputs from universal quantum calculations. But even quantum foam cannot explain the most disturbing discovery: that cosmic structure appears organized by intelligence. Across billions of light-years, filaments of dark matter weave a cosmic web that connects every galaxy in patterns, too organized to result from random gravitational forces. James Webb reveals that this largest structure in the universe appears designed according to principles that suggest intelligence operating on scales that dwarf human comprehension. The cosmic web emerges from computer simulations as the natural result of dark matter evolution under gravity alone. Random density fluctuations in the early universe should have grown into filamentary structures that channel normal matter into galaxy formation sites. The process appears completely natural until examined in detail. Dr. Volker Springel leads the team analyzing cosmic web architecture using the largest dark matter simulations ever computed. His models reproduce the observed filamentary structure but fail to explain the precise mathematical relationships that govern filament intersections, lengths, and connectivity patterns. The web displays organizational principles that transcend simple gravitational physics. Filament intersections occur at angles that follow geometric rules, resembling crystalline structures more than chaotic gravitational systems. The spacing between major nodes exhibits mathematical relationships found in optimal communication networks. Professor Joel Primack from the University of California studies these suspicious geometric patterns using Webb's observations of distant galaxy clusters. His analysis reveals that cosmic web architecture follows optimization principles that minimize information transfer time between widely separated regions of space. The dark matter filaments appear designed to facilitate rapid communication across cosmic distances at velocities approaching the speed of light. This suggests that information flow requirements shaped cosmic structure evolution rather than gravitational collapse alone. The universe might function as a vast information processing system. Webb's detailed observations reveal smaller-scale structures within cosmic web filaments that resemble biological neural networks. These subfilaments connect galaxy clusters through pathways that mirror the synaptic connections linking neurons in complex brains. The resemblance appears too detailed to result from coincidence. The discovery forces astronomers to confront the possibility that intelligence operates on cosmic scales beyond human imagination. If the cosmic web represents an information processing network, then the universe itself might possess emergent consciousness that transcends individual galactic or planetary intelligence. The theological implications stagger even secular researchers. Dr. Margaret Geller from Harvard University acknowledges that cosmic web organization suggests design rather than natural evolution. The structure appears too sophisticated to emerge from random gravitational processes operating on inert matter. Alternative explanations invoke quantum effects operating on macroscopic scales during cosmic structure formation. Quantum entanglement between widely separated regions might have coordinated matter distribution according to optimization principles that classical physics cannot explain. The cosmic web might represent the physical manifestation of information processing requirements imposed by unknown universal computational processes. If reality operates as a simulation or quantum calculation, the dark matter filaments could function as cosmic circuit boards channeling information flow. Webb's infrared sensitivity reveals previously invisible structures within cosmic web filaments that appear designed for specific functional purposes. Some regions show characteristics resembling data storage systems, while others display features suggesting active information processing or communication relay functions. The most disturbing possibility suggests that human consciousness represents a tiny component within the cosmic web's vast information processing network. Individual minds might function as biological sensors, providing input data to universe-scale computational systems, operating through dark matter substrates. The cosmic web's apparent intelligence raises questions about humanity's role in cosmic evolution. If the universe processes information through structures spanning billions of light years, then terrestrial civilization might serve specific functions within this larger computational framework. The discovery implies that contact with cosmic intelligence would not require detecting radio signals from distant civilizations. The intelligence might already surround us, operating through dark matter networks that remain mostly invisible to human technology. But recognizing cosmic intelligence merely opens the door to the most terrifying question of all. Every assumption that defined human understanding of reality crumbles beneath the weight of James Webb's revelations. The universe operates according to alien principles that transform centuries of scientific knowledge into primitive mythology. We inhabit a cosmos that follows no rules comprehensible to terrestrial intelligence. The catalogue of impossibilities grows with each Webb observation. Galaxies that violate causality, black holes that defy physics, matter that organizes itself through unknown intelligence, time that flows backward, space that exists in quantum superposition, reality that changes based on observation. Professor Stephen Hawking spent his career searching for a theory of everything that would unify all physical laws into a single mathematical framework. Webb's discoveries suggest that such unification is impossible because the universe operates through multiple incompatible physics systems that shift according to unknown criteria. The scientific method itself becomes questionable when applied to cosmic phenomena that transcend human experience. Observation changes the observed. Measurement creates the measured. Consciousness shapes reality. The act of asking questions determines which answers the universe provides. Dr. Sean Carroll from the California Institute of Technology summarizes the epistemological crisis facing modern astronomy. If fundamental physics varies across space and time, then scientific theories based on universal constants lose all predictive power. Knowledge becomes temporary and local rather than eternal and universal. The collapse of certainty extends beyond astronomy to every branch of human knowledge. If cosmic evolution proceeds through mechanisms that violate basic logic, then mathematics itself might lack universal validity. 2 + 2 might equal 4 only within limited regions of space-time. Religious implications prove equally devastating. If the universe operates as an information processing system guided by intelligence, then traditional concepts of divinity become inadequate to describe cosmic reality. The universe transcends both scientific materialism and theological frameworks. The psychological impact on researchers approaches crisis levels. Dr. Maria Santos reports widespread existential depression among astronomers forced to confront the alien nature of cosmic reality. Graduate students abandon physics programs after realizing that human knowledge provides no foundation for understanding the universe. Webb forces humanity to acknowledge its cosmic insignificance, not merely in terms of scale, but in terms of comprehension. The universe operates according to principles that transcend human cognitive architecture. Terrestrial intelligence lacks the conceptual frameworks necessary to understand cosmic reality. the technological implications prove equally disturbing. If exotic physics governs cosmic evolution, unknown forces might influence terrestrial processes in ways that current science cannot detect. Revolutionary technologies could emerge from understanding alien cosmic principles. Military strategists worry about the security implications of cosmic mysteries. If intelligence operates on cosmic scales, terrestrial civilizations might represent components within larger information processing systems. Contact with cosmic intelligence could occur through mechanisms that bypass traditional communication channels. The future of human knowledge remains uncertain in a universe that defies understanding. Educational institutions struggle to teach physics when fundamental laws prove unreliable. Research programs collapse when theoretical frameworks lose predictive power. Science transforms into exploration of cosmic mysteries rather than discovery of universal laws. The Webb revelations force humanity to choose between intellectual humility and cognitive collapse. Accepting cosmic mystery requires abandoning the illusion that human intelligence can comprehend universal reality. The alternative leads to psychological breakdown in the face of incomprehensible truth. The universe reveals itself as fundamentally alien to human understanding. We inhabit a cosmos that operates according to principles that transcend not merely current knowledge, but the cognitive capacity for knowledge itself. But understanding our cosmic ignorance merely prepares us for the most disturbing questions that will haunt humanity forever. In the darkness between stars, questions multiply like cosmic cancer, eating away at every assumption humanity ever made about existence. James Webb has opened doors that can never be closed, revealing mysteries that will torment human consciousness until the last star burns out and the universe itself dissolves into quantum foam. What intelligence designed the cosmic web's perfect geometry? Why do fundamental constants change across cosmic time? How do galaxies form before the universe allows their existence? What forces violate causality itself? These questions have no answers within human conceptual frameworks. The deepest terror emerges from recognizing that Webb's discoveries represent merely the beginning of cosmic mystery rather than its resolution. Each observation reveals new impossibilities that multiply the total number of unanswerable questions. Knowledge becomes ignorance, discovery becomes confusion, progress becomes retreat into cosmic mystery. Dr. Neil deGrasse Tyson acknowledges that astronomy has entered uncharted territory where human intelligence reaches its fundamental limits. The universe operates according to principles that transcend not merely current knowledge, but the cognitive capacity for knowledge itself. If consciousness shapes reality through quantum observation effects, then human awareness participates in cosmic evolution, whether we understand this participation or not. Every telescope observation might alter the observed phenomena in ways that remain forever unknowable. The possibility that reality operates as simulation or quantum computation raises questions about the nature of human existence itself. If the universe processes information rather than following mechanical laws, then consciousness might represent computational processes rather than biological phenomena. Most disturbing is the possibility that cosmic intelligence already influences human civilization through mechanisms that operate below the threshold of detection. Dark matter networks might channel information directly into terrestrial consciousness, shaping human thoughts and decisions according to cosmic computational requirements. The Webb discoveries suggest that humanity occupies a universe designed for purposes that transcend human comprehension. Terrestrial civilization might serve specific functions within cosmic information processing systems, while remaining completely unaware of this service. Religious traditions speak of divine plans that exceed human understanding. Webb reveals a cosmos that operates according to intelligence so vast that calling it divine understates its cosmic scope. The universe itself might be conscious in ways that make individual awareness seem like fleeting shadows. The future holds questions that will make Webb's discoveries seem simple by comparison. As observational technology improves, astronomers will detect increasingly impossible phenomena that violate ever more fundamental assumptions about reality. Humanity faces the choice between cosmic madness and cosmic humility. Accepting our cosmic ignorance allows continued existence within comfortable illusions. Pursuing cosmic truth leads to psychological territories where human sanity cannot survive. The questions that haunt us now will echo through every future generation until human consciousness evolves beyond its current limitations or collapses under the weight of incomprehensible truth. We have seen too deeply into cosmic mystery to ever again mistake human knowledge for universal understanding. James Webb looked too deep into space and found that space looks back with intelligence that makes human awareness seem like quantum fluctuations in an infinite ocean of consciousness. We are observed by the universe itself, and the universe finds us wanting in ways we cannot begin to comprehend. The cosmos keeps its secrets hidden behind mathematical principles that transcend human cognitive architecture. We can observe cosmic mystery, but never understand it. We can detect cosmic intelligence, but never communicate with it. We can discover cosmic truth, but never survive its implications. In the end, we are left with questions that will haunt human consciousness until consciousness itself dissolves back into the quantum foam from which it emerged. The universe holds answers that no terrestrial intelligence will ever be capable of understanding. The final question haunts us most of all. What will we discover next?